And next up for talks, we have Ankur Desai, who's going to tell us about, oh, and I didn't switch quick enough to his title, perspectives on the power of data sharing and synthesis in a grassroots ecosystem monitoring network. Go ahead, Ankur.
Thank you, Sarah. And let me start some slides here. Okay. Thank you, Sarah. Thank you, Malia, too. That was a really fascinating talk. And there's some really fascinating parallels to lots of things we've been doing in climate science and climate science communication for many, many years. And some of your tips are things I think I'm going to think more about as I engage. But for something completely different, I'll talk a little bit about some of the work we're doing. So 60 times a second on a 130-foot tall tower that I helped build in the middle of the woods of Michigan, a device that looks like a claw called a sonic anemometer records the time it takes a pulse of sound to get from one claw to the other for each of the 3 pairs of claw fingers. For the difference in time transit of each and knowing the speed of sound and how that varies, the anemometer's microprocessor calculates air temperature and wind velocity. Every 10th of a second, that value is averaged and sent as an analog electrical signal to a small computer called a data logger. The data logger converts the signal to a number and stores it on memory. Every hour, it sends all these values out another wire up to an antenna and out a cellular 4G data signal to a computer sitting in a room in the Atmospheric, Oceanic, and Space Science building here at UW's campus. Every night, a collection of scripts written in a variety of 4th-generation scripting and analysis languages sorts, reads, quality controls the data files. It combines the observations of others and applies a variety of equations and filters to calculate the half-hourly observations, which are then uploaded to the Department of Energy server in California, where a quality control script accepts or rejects whether the data meets stringent format and range criteria, and every couple of months, further processing is made, and then the data are hosted on a website with open Creative Commons license and a common API for access by all of you. I share this journey of a single data point because in our automated world, so much of it is hidden, and yet every single step of every data point is curated in some ways by humans. People like here, like our instrument vendors who run calibrations and update firmware, as demonstrated at a summer school. People like lab managers like Jonathan here, who climbs the tower and maintains the instruments. Like our graduate students in the lab, here's Amara, who reviews quick look pots and watches for outliers and gaps. Like me, who writes the scripts and verifies the calculations, or my colleagues at DOE, the scientists who define the criteria and review what's necessary for hosting data. And like all of those who download and use, and perhaps if I'm lucky, tell me the cool things or the problems they found with these data, whether that's exploring time series across space and time, regressing sites for long time periods against hypothesized drivers, or confronting the observations of models like the students here are doing in this photo at a graduate summer school that I teach at. Today, there are more than 1,000 of these towers around the world, as this crowdsourced image shows. Sonic Anemometry, an instrument whose original design was pioneered here at the University of Wisconsin by Werner Sumi, who later went on to develop the world's first weather satellite and found our campus's Space Science and Engineering Center. This is an instrument that is one of dozens of others, along with, that form the basis of our climate observatories. Sonic anemometry, combined with infrared spectroscopy, is one of the ways that we learn how atmospheric turbulent motions transfer heat, water, momentum, carbon dioxide, and methane from ecosystems to the atmosphere, and from atmospheres to the ecosystem. So why does that matter? Well, it matters because this is the fundamental functioning of our Earth system. Moreover, it matters even more because the climate is changing faster than any time in recent past by greenhouse gas emissions of fossil fuel and also from deforestation. And ecosystems in the land and ocean respond to that and modulate that through photosynthesis, offsetting nearly half of all our fossil fuel emissions every year. We can see that in space, like in this animation from NASA, where the differences in reflected, visible, and emitted infrared wavelengths of light relate to plant activity through the year. But the breathing of the biosphere is highly dynamic in space and time, and predictions of its futures are fraught with uncertainty. Careful, calibrated baseline observations are the benchmark on which satellite observations or future climate projections, as seen here collected with past climate observations, rest. A lot of these ecosystem climate observing sites are now part of a global collection of distributed bottom-up networks called FluxNet that forms an observing system backbone. Many of us share our data. Many of us share data freely early on. For myself, when I was a graduate student, sometimes for convenience. Most of the time, it led to new collaborations. And in fact, in many cases, some of my most influential papers. So why 10 years ago did I ask an editor to retract a paper that actually used these open data and that told an important climate change story? Back then, one day, I opened up my inbox to a table of contents alert. I found a paper that told an important story with these data about changing rates of decomposition and carbon dioxide emissions. It was really good. And then I looked at the lengthy author list and I noticed I was a co-author on it. But I've never seen this paper before. I never agreed to this. The paper has some inconsistencies to it. The author chose to include many data providers, though they were not obligated to. But the author failed to actually include them in the analysis and the writing. And after some back and forth with other authors in the same position, we asked for a retraction and the editor agreed. The lead author, a postdoc, was of course taken aback, but this story has a happy ending. The postdoc and her supervisor stepped it up, brought on the data providers, developed an opt-in co-authorship after reviews and edits. The paper was republished in the same journal, and climate observations went on to live another day, telling another important finding. We've learned a lot since then on how including folks who make the observations is critical, even when it's automated, in any data science type research. Over the years, through annual community meetings and discussions of international teams, for example, shown in key meetings in this timeline, the community developed a fair use policy and a choice of licenses for data providers. It didn't come easy. Some folks were more reticent to share than others. It never worked when it was imposed from above without input from data and providers. It had to be hammered out, discussed, experimented, and tweaked. It's important to note that the funding for these observations was also distributed, not from any one single agency. We were all submitting data out of a sense of obligation to support synthesis for climate. We were a coalition of the willing. Today, when data are downloaded, users acknowledge this policy and the principal investigators get an automated email with this download notification. Data submissions have metadata files, digital object identifiers and site identifiers, and citations for descriptions of instruments organized through a management contract from the Department of Energy awarded to one of its national labs. Authors aren't required to engage PIs for manuscripts or require co-authorship, but they're asked to consider reaching out. And many new synthesis groups that have occurred since this time are often use these policies and enhance it and build on it. New observing networks that are using this network as a model. So that's the message I want to share. Here's another beautiful wetland site that I want to share at this Data Bazaar. No observation that you're using in data science research is made without human input somewhere in its design, in its maintenance, in its processing, in its quality control, in its serving and hosting. How you incorporate those people and how you develop data policies is essential in any research that moves forward. And it needs to be humane and designed from the ground up. And when you do that, you can learn a lot of amazing things. You can learn how, for example, rising CO2 is making forests more efficient in the amount of water transpired per unit carbon dioxide gained. And as a result, grow faster and sequester more carbon, but only up to a point. Or you might learn by long-term observations distributed across a continent, how early springs, in the case of the 2012, for example, in a warming climate, enhances meteorological summer droughts that we saw, for example, later last summer. This depends on how early plants bloom, which in turn depletes soil water. And it's something we can see in these observing sites once they had multiple years of data. And we can continue to build on that in the case of a graduate student in our lab, Amara, who's been working on machine learning tools for predicting crop yield and evapotranspiration using these data sets in a variety of ways to forecast the future and help improve irrigation practices on farms, as shown in here for our work on corn, soybeans, and potatoes in the Midwest. Or we might learn something fundamental about how evolution has shaped ecosystems along certain axes of function that is mediated by structure, and what that implies about ecological resilience in a changing climate, as in this recently published paper where hundreds of sites were integrated. So grassroots, both figurative and literal in my case, maintain baseline observations here, whether it's bottom up, as shown in this figure here from this paper, or more coordinated networks that have now come online, like the National Ecological Observatory Network or the Critical Zone Observatories. Care and feeding of these roots is required for a healthy ecosystem. So with that, that's kind of what I wanted to share with you today. I hope you got a sense of what it means to make observations from the ground up for those of us in climate science, and hope that you will think about these in your own work as you think about where the data you use comes from and how you incorporate the folks who make those observations possible. Thank you.
Thank you, Ankur. There's no questions in the chat yet. Please put your questions if you have any questions for Ankur. I will ask one of my questions is, you described a couple of different networks and some of the challenges in building up those networks and that they face. And I saw that there's like NEON, LTER, Ameriflux all listed. How do these organizations work together, and what are the current challenges the community faces in bringing people and their research together?
That's great. So that's a great question. So these networks are, they all have slightly different goals. They have different levels of centralization. But one of the things they do have is overlap in people who are interested and invested in the data. That's led to the formation of things like working groups. One of the big challenges is interoperability, right? So making sure that the same types of data collected in NEON, which is focused on ecological baseline observations, but collects the same types of flux data that we do in Ameriflux, can share and be usable together, right? So power of synthesis is in bringing large amounts of data together. And so there's been ways to define standards, ways to be able to submit data sets to multiple repositories, so that even though there's a primary repository, NEON data the flux data is also in Ameriflux in the Ameriflux data format following the Ameriflux data policy. And that had to be hammered out and discussed.
Thank you. Let's give Ankur a thank you with our reaction option for round of applause. Yeah. See everyone. Oh, there is a question from Michael Ferris. Are particular tools or practice useful, or practices useful, I think, in sharing the data is what I'm guessing. Michael, do you want to add to that question?
What are particular practices or tools or techniques or processes most useful? I think in typing it quickly, I left out the word most.
Yeah, that's a good question. I think a little bit about the summer school we teach, where we train scientists to do synthesis with our data sets. And, one of the things that we do find is that, we are seeing this shift away from people downloading data and unzipping it and moving toward application programming interfaces, bringing their code to the data, using Jupyter notebooks and the like, and having tutorials and processes and dragging those of us who are old along into this new way that we deal with data and work with it is pretty important.
I think you still have a little time. So there's another question in the chat here. Can you please tell me a little bit more about your data collection practices? What are the analytics tools that you use to create the visualizations for this presentation in particular?
Okay, for the presentation, that's a good one. As I mentioned, we use a variety of programming languages, a lot of Python and R. I still use a lot of IDL because that's what I did my PhD in. But my lab manager for kind of raw data quality control and ingest, we have a variety of Python-based packages and databases, as well as a company called Grafana that provides real-time visualizations of data streams. That we have installed on our server that we use quite a bit for quick looks and for identifying problems in the data. A lot of the other tools have been kind of hand-built, partly through the Ameriflux program that have been shared freely. I can share with you a blog post that Jonathan actually wrote and submitted on Ameriflux that goes through the entire workflow that he uses for the quality control steps that go from data collection to data hosting. And that kind of goes quite into the weeds of how the database actually works. I think it would give you a good answer to your question there. In terms of the specific figures here, they're coming from all over the place. So I can't tell you any one particular one.
Question from Heather. Have there been collaborations with Indigenous communities in collecting and sharing data?
Yeah, there has been some, and a couple of my colleagues, including Professor Paul Stoy here, who's a faculty member at UW in Biological Systems Engineering, for example, is working with the Menominee Nation on doing eddy covariance measurements of carbon, similar to the things I discussed, to look at emerald ash borer outbreaks and the impact that's having on the forestry operations there. As data sovereignty becomes a important piece of that discussion, as well as kind of working in true partnerships. I have only worked in education on training on that side, but there have been groups involved. Particularly, there's a large number of folks of the tower network that's based in Alaska that I think has a lot of experience with that through a particularly large NASA project that was done in conjunction with Arctic indigenous communities.
All right, we're coming to the end of our time, so sorry. There is one more question in chat if you'd like to answer it, but thank you, Malia and Ankur, for sharing.